In this lesson, we're going to start learning the basics of how we determine what the structure of a covalent compound actually looks like. So the system that we use to represent the structures of covalent compounds is known as Lewis electron dot structures, or sometimes Lewis dot structures, or just Lewis structures is usually what I go with. And what these are meant to convey or show is how atoms are connected and where all of the valence electrons are. In a covalent compound, in a covalent molecule. We'll go with compound. So these are meant to really just show us the connectivity and how the electrons are arranged. They don't actually show us the three-dimensional shape, and we'll get into how we figure that out a while later in the unit. For now, focusing on connectivity, and then we'll figure out how that translates into an actual shape later on. So in these types of representations, there are two essential types of electrons that we need to be able to represent. There are the bonding electrons, which are the electrons that are shared between atoms in a bond, so shared between bonded atoms. And these are always shared in pairs. So one covalent bond always contains two electrons. And in our Lewis structures, we represent bonding electrons as a line between the bonded atoms. So you may have seen the structure of a water molecule before. It looks something like this. The shape is sometimes represented a little bit differently, but again, Lewis structures aren't meant to show us the shape. So our bonding electrons, the ones that are actually holding these atoms together, are the ones that we're drawing as lines connecting the oxygen and the hydrogen. So this line represents two electrons that are being shared between the hydrogen atom on the left and the oxygen in the middle. And this line represents a different two electrons that are being shared between the hydrogen on the right and the oxygen in the middle. So our bonding electrons are those lines that we highlighted in yellow. We also have non-bonding electrons. So these electrons are not shared. They're only on one atom. These also usually come in pairs, but they don't technically have to. So these pairs of non-bonding electrons are referred to as lone pairs. And we represent these as dots in our Lewis structures. So to use water as an example again, there are non-bonding electrons present on the oxygen atom in water. So the hydrogens don't have any. But the oxygen has two lone pairs, or a total of 4 non-bonding electrons that it has complete ownership of, and it's not sharing with any other atoms. So those two lone pairs are completely on oxygen, no sharing going on there. So these are the two types of electrons that are going to be represented in our structures. And to come up with these structures, to build a structure like water and figure out where all of the electrons go, there is a step-by-step process that we can use that will get us to our destination, get us to our goal here of being able to draw a valid structure that kind of follows all the rules that we need it to follow. So there are kind of a lot of what-if situations, a lot of ifs, ands, and buts to this process. So we're going to start with really simple molecules, and then we'll tackle some of those what-if situations in future lessons. So I have the process kind of written out down here already, so you may need to do some pausing to copy stuff down if I'm moving a little bit faster through this part. But I want to be able to use this to do a couple examples, because if you follow this process, pretty much no matter the molecule, there are a few weird exceptions, again, we'll get into later, but for the most part, no matter the molecule, this will end you up at a valid structure. So our process for drawing Lewis structures, step one, first thing we always need to do is determine the number of valence electrons that are going to be present in our structure. We said earlier that a Lewis structure was supposed to show us where all of the valence electrons are, which means one of the first things we need to know is how many are there, how many electrons need to be represented in my structure in order for it to have the right number. So thankfully, this is pretty easy to determine. The group number of your element on the periodic table is equal to the number of valence electrons that it contributes to the structure of the molecule. So the group numbers we're referring to are specifically the ones for the A group elements, 1 through 8, skipping over the transition metals. So those numbers are equal to how many that a given atom is going to contribute. So we're going to work through an example step by step. We are going to do the molecule OCl2. So if we want to figure out how many valence electrons are going to be in this molecule, we first need to identify where these elements are on the periodic table. So oxygen is right here in group 6. Chlorine is below it in over a column in group 7. So that means that my oxygen atom is going to bring 6 valence electrons to this Lewis structure party, and my chlorine is going to bring 7 for each chlorine atom. And remember that that subscript is telling me that there are 2 chlorine atoms in this formula. So I'm going to have 6 plus 7 times 2, which gets me a total of 20 valence electrons. So what this means is that my final structure, when all is said and done, must have exactly 20 electrons represented in it, no more, no less. If you do not have exactly 20 electrons, you have not actually drawn the structure for the correct molecule. You've drawn the structure for something with a different charge. If you have extra electrons, that would mean it's an anion. If you have too few electrons, that would mean it's a cation, but it's not actually the structure that we're going for. So once we've determined the number of valence electrons in our structure, we need to determine sort of what our framework is going to look like. So generally, we will be dealing with pretty simple molecules that have one atom in the center and everything else arranged around that. And we need to pick out which element is going to go in the middle. And usually, it's going to be what I like to refer to as the unique atom, or the one-of-a-kind atom, something that there is only one of in the formula. So looking at this formula, for the example that we're working through here, for OCl2, there are 2 chlorine atoms. So chlorine is not unique in this formula. It is not one of a kind, but there is only one oxygen atom. So that's all I mean when I am referring to something as a unique atom, is that its invisible subscript is 1. In the event you have multiple unique atoms, the least electronegative element is generally going to be the central atom, and also note that hydrogen can never be a central atom. The reason for that is that its valence shell is the n equals 1, which only contains a single s orbital, and therefore its valence shell can only hold 2 electrons. One bond contains 2 electrons, so hydrogen can only form one bond at a time, so it can't be like in the middle between multiple things forming multiple bonds. So for this example, we can pretty easily identify oxygen as our unique atom, so that's going to be the one that we put in the middle and connect everything else around that. And then the next step is to actually do that, to arrange our atoms and connect them with bonds. So we're going to put our central atom in the center. We're going to put a bond to a chlorine on one side, a bond to the other chlorine on the other side, just to kind of set up our skeleton and start connecting things a little bit. From here, actually, let's do this whole thing. The next thing we're going to do is start to fill up valence shells. So the reason why things bond, as we've talked about, is to become more stable. And things are generally most stable when they have filled valence shells. So that's kind of the goal of drawing our Lewis structures, is to figure out what arrangement of atoms and electrons is the most stable, because that's how that collection of atoms and electrons is most likely to exist. So the next thing we're going to do is start adding lone pairs to our peripheral atoms, aka not the central atom, until their valence shells are completely full. So a full valence shell for the vast majority of elements is considered to be 8 electrons, or what is often referred to as an octet. You will often see this idea referred to as the Octet Rule. There are lots of exceptions to the Octet Rule. The Octet Rule was meant to be broken, except when it's not. And peripheral atoms pretty much don't break the Octet Rule. You will just about always have a filled valence shell of 8 electrons on all peripheral atoms, with the exception of hydrogen. Again, as I mentioned, it can only have a maximum of 2 because its valence shell is the n equals 1. So for everything else, we're looking to get to a total of 8 electrons, including bonding and non-bonding electrons that are available to that atom. So our peripheral atoms, let's make this bigger, our peripheral atoms in this structure are the chlorines. So we are currently adding electrons, adding lone pairs to the chlorine atoms until their valence shells are filled. So currently, each of these chlorine atoms is involved in a bond. It is sharing those bonding electrons with the oxygen in the center, but it has access to them. So both of those electrons count as filling the valence shell of chlorine. They also count as filling the valence shell of oxygen, and that's what the sharing is all about. That when these electrons are being shared, they're essentially counting towards the valence shells of 2 atoms at once. So we've got 2 electrons here for the chlorine on the right, we've got 2 electrons here for the chlorine on the left, and we're looking to get to 8 total for each. So to do that, we're going to add lone pairs. Specifically, we're going to add 3 lone pairs, or a total of 6 non-bonding electrons, to the 2 bonding electrons that were already there to get us to our total of 8. So each of my chlorine atoms has 2 bonding plus 6 non-bonding electrons. That is getting us to our total of 8 valence electrons, to that atom's valence shell being filled. So once we've accomplished that, we want to kind of check in on how many electrons have we added to this structure so far. So remembering that each of our bonds is 2, we've got 2 plus 2 is 4, 6, 8, 10, 12, 14, 16. So currently, I wanted you to change color. Red. There we go. Currently, we are at 16 electrons. We determined earlier that our end goal was 20. So we have 4 electrons left to place. And what we are going to do is place those electrons on the only place we have left, which is the central atom. We filled up the valence shells of our peripheral atoms, but we have not done that for the central atom yet. So we still need 4 more electrons. Those 4 electrons are going to be added as lone pairs on my central atom. If you reach this stage and you're already out of electrons, you won't have any lone pairs on your central atom, and that's totally fine. If we had hit 20 up here, we would basically be done at this point and just checking over our structure. In this case, we didn't. We needed to add 4 more. The place where we have space for those left is on our central atom. So at this point, we have added all of our electrons. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 electrons in our structure, which is what we were aiming for. So the last thing we need to do is just kind of check everything over and make sure that all of our valence shells are filled. So we come back here. Remembering that shared electrons count towards the valence electrons of both atoms in the bond means that chlorine, each of our chlorines, has access to the 3 lone pairs on it, plus the electrons in this bond. So that gives us 2, 4, 6, 8, 2, 4, 6, 8. Filled octets on both of those are good to go. And then this oxygen in the middle also has access to these bonding electrons in both bonds, as well as the 2 lone pairs, or 4 non-bonding electrons. So we've got 4 bonding plus 4 non-bonding, also for a total of 8, to make that octet of electrons that we're looking for, that corresponds to a filled valence shell, specifically filled S and P valence subshells is what we're looking at here. So this structure is done. At this point, if you find that you do not have filled valence shells, there are things you can do to fix that. That is a subject for a future lesson. For now, I want to go do one more simple example where this much of the process is enough. So we're going to walk step by step again through these same processes, or through this same process, but I would like you to try it on your own first. So see if you can apply the same ideas to draw the structure of NCl3. So pause here, take a few minutes, walk step by step through the same stuff, and then we will talk about it. So again, we are going to start off by figuring out how many valence electrons need to be represented in this structure. Nitrogen is in group 5, so that is going to bring 5 electrons. Chlorine is going to bring 7 from each atom, and there are 3. So that is going to give us a total of 26 electrons that we are looking for here. In this formula, we once again have a pretty easy to identify unique atom, one-of-a-kind atom. There's only 1 atom of nitrogen compared to 3 of the chlorine. So the nitrogen is going to go in the middle. And then we can start to connect the dots here. So we'll put our central atom in the middle and connect all of the chlorines around it. Note that exactly how you arrange the peripheral atoms doesn't matter. So it is common that a lot of people will do it really symmetrically just because humans like symmetry, but it doesn't actually matter. Central nitrogen bonded to 3 peripheral chlorines is all that matters. If they're like up, down, left, or right, makes no difference. Because that's just not what Lewis structures are intended to show. They show the connectivity, not the actual three-dimensional arrangement. So now we can start adding more electrons to our structure by filling up my peripheral atoms. Snag this friend. There we go. So we are once again looking to fill up our peripheral atoms first. Each of those is currently involved in one bond, which means that each of them currently has 2 valence electrons as our structure is drawn. So we need to add 6 more, just like we did last time, in the form of 3 lone pairs on each of our chlorine atoms. So our chlorines all now have filled valence shells of 8 electrons. They have complete octets. So we can sort of check in on how many electrons we have so far to see how many we have left to use in the next step. So we currently have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We were aiming for 26, so we need to add 2 more electrons to our structure. And we are going to do that by adding them to our central atom. So our central atom gets whatever we have left, regardless of how many that is. There's no place else for them to go except on the central atom. So we can put a lone pair on our central atom there, which gets us to the 26 electrons that we were looking for. So this structure is quite possibly complete. And we just want to check things over and make sure that all of our valence shells are in fact filled. So we have the chlorines have their 3 lone pairs plus the bonding electrons. Try and keep this as neat as I can. The redo? Yes. The nitrogen has its one non-bonding pair, plus it has access to all 3 of those bonding pairs. So our chlorines have 6 non-bonding plus 2 bonding for a total of 8 each. Our nitrogen has 2 non-bonding plus 6 bonding for a total of 8. So all of these all of these atoms do have filled octets. So this structure is complete and correct as well.